So this is going to be just a walkthrough of how high-level synthesis systems work and how specifically a demonstration high-level synthesis program that I've been working on that uses LLVM works. So I'm just going to go over the general ideas of how high-level synthesis tools, which translate languages like C and C++ into hardware, work. And I'm going to do that by showing basically how they translate a normal compiler intermediate representation into Verilog or another hardware description language. So to get started, let's just start with a really simple example, and that's a program that stores a constant to memory. So let's just take a look inside. So I'm in the DHLS repo on my local machine. Let's just take a look inside the example program we're going to work with, and it's this program called single store, and it's a void C++ or C function, and all it does is take in a pointer, which is a restrict pointer. You can actually just ignore this restrict here for a while. It's just a compiler directive. And all it's going to do is store the value 5 to the 0th entry of whatever A is pointing to. So we're going to use this as a first example of how to do high-level synthesis. So before we actually get into high-level synthesis, there's two big semantics problems. The first one is that basically there's a lot of missing information, right? What makes high-level languages high-level is that they're deliberately agnostic about a lot of the things that you need to know if you're going to create hardware. So for example, just in this program, how long does a store take, right? How many cycles does a store take? And where is A in memory, right? So in normal C and software, A is a pointer. It's a number that represents a location in a single unified address space. In hardware, you can have physically separate SRAMs, right? What RAM is A in, and how do we read it, and how many read and write ports does this RAM that A is contained in have? C and C++ and other high-level languages don't say anything about these kinds of limits. And the other one is backwards compatibility, right? So C and C++ and all other high-level languages already have a semantics. So if your high-level synthesis system is going to be useful, the extra information that you graft onto programs when you try to synthesize them to hardware has to be consistent with the semantics that's already there. And obviously, if it wasn't consistent, then when you ran the program as C and tried to do verification, you could get different results than when you finally synthesized hardware, and so the tool would be useless. So we've got to be careful to be consistent. So there's two things we're going to do to resolve these problems, right? The first one is we're just going to add in extra data structures that describe resource limitations, limits on the number of resources we have. Getting hiccups here, sorry. The operation latencies, the memory layout, and in more sophisticated systems, stuff like initiation intervals with built-in functional units and things like that. And then for backwards compatibility, we're really only going to support a pretty limited subset of C. So the function that we're going to convert is going to represent a hardware module, and we're going to say that the return value has to be void. We could make the return value the output of the module, but that's a little bit limiting. You might have and it's just kind of logically inconvenient. So the way we're going to express inputs and outputs to this synthesized module is through pointer arguments to the function. So in this case, for example, we only ever write to the pointer A, so A is an output. And if we were to, read from it, it would be an input and an output, so it'd be an in-out. If we only ever read from it, it'd be an input. Then we're going to assume for now that the arguments are going to be restrict pointers, and the pointers are going to represent locations or contiguous regions in RAMs connected to the module that we're going to synthesize. So to show that visually, basically we're going to have our simple program. Here's the same program, single store. Then we're going to add some extra data structures through a C++ API that describe where A is in memory. So in this case, we're going to say A is range 0 to 4 in this external RAM. So here's the module we're going to synthesize from our function, and I'm not showing what the contents are. And the module is connected to this RAM that contains A, and it also has a valid signal that says when it's done. And for now, we're going to say there's no resource limits. We're going to say that stores take 3 cycles to complete, and that's all the extra information we need for now. It's also just worth saying, so what does it actually mean for the synthesized Verilog to match the behavior of a C program? And in this system, what I'm going to say it means is basically when the valid signal of the generated module is high, the contents of the RAM regions that we're in the RAM that we're connected to, or the synthesized module is connected to, every function argument, every pointer argument basically, has to, in that RAM, have values that match the values you would see in the corresponding memory regions in C software. And by the way, this does mean that we're not going to support things like precise interrupts when this module is running. So basically, the module has a valid signal. When valid is low, anything about the internal state of the module could be true. when valid is high, the output looks like what we'd expect in C. So for example, when valid equals 1 in single store, we'd expect that the 0th entry of A, which is this highlighted region, will be 5. Okay, so what do we actually have to do to translate a sequential program like this into hardware? Basically, there's 3 steps, and the first step is just like what you'd see in a normal compiler. So we're going to take a C program, we're going to pass it into Clang, and Clang is going to convert that into LLVM, and nothing really fancy or special is going to happen there. Then in the middle is the meat of the high-level synthesis program, and it's called the scheduler. And basically, we're going to pass in the extra data structures, these guys, the memory layout, resource limits, and completion times, into the scheduler along with an LLVM program that we got out of Clang. And the scheduler is going to produce a state transition graph, which is basically just a finite state machine that represents the custom hardware we're going to generate. And we're going to feed that into an elaborator that's going to produce Verilog. You could also produce VHDL or another language. And the elaborator is important, but it's conceptually kind of boring, and I'm going to focus on the scheduler. The elaborator is really just filling in details in this finite state machine and generating a specific hardware description language. Okay, so actually before I go into the details of what the scheduler is, maybe it'd be good to just look at a real example. So we've got this single store file, and in the test scheduling files, so if you go into the DHLS top level directory and look around and you go to test scheduling, it's a large file, and it contains a bunch of unit tests of the system. So here's the unit test for scheduling the single store program. And the structure of it is basically, first we're going to use LLVM to load the module, which is really just the file that contains the program or the function we want to synthesize. And then we're going to find the function in that module. So this load module single store and then get function single store is really calling Clang on this single store function. So let's run this. And by the way, this is just the test underscore case thing is just the unit testing framework's notation for a test case. So let's just run this one test case. And so what we see is, you can ignore that error. That's something that shows up in the first line of the test bench no matter what. It's actually not an error. It's just a printout I need to get rid of. But so the test passed, and we've got a custom state machine from our tool. And here's the actual LLVM function that comes out of this single store C program. You can also see the function in test LL files single store.ll. It's the same thing. And if you look at this function, it basically has 2 instructions. We're going to store the value 5, and it's a 32-bit value, to the location pointed to by A, and then we're going to return. So conceptually, this is going to send data to the RAM that we're going to connect our module to, and then return is going to set the valid bit to be high. And that's the basic, that's the LLVM program that we're actually going to translate. It's this 2-instruction program. And this cout LLVM function and then printing out the function is actually in the test bench output here. Okay, I'll turn that annoying sound off. And here are our data structures, right? So we've got the hardware constraints. We set the latency of stores to be 3. We say that the getArgF0 just means get the first argument of the LLVM function. In this case, it's A. And say that that guy starts at RAM location 0. And then we're going to call the scheduler to schedule the function. In this case, it's a unit test, so I know that this function should have 4 states, but you can ignore that for now, and we do some more unit testing. Then we build the STG, so the call up here to create this function really represents running Clang to produce the LLVM program. Then we create our hardware constraints, and we schedule the function. That's the scheduler. Then we build this STG. STG is short for state transition graph. And that's what's going to come out of here. So really 2 steps are inside of here in the API. I could clean that up a little bit. And then we're going to emit Verilog. And the emit Verilog is basically the elaboration of the state transition graph into real Verilog, basically into a text string that we can feed out into a file and simulate. And then this final run iVerilog test bench is going to run a test bench that I hand wrote to test that the single store operation actually works. So in the next video, we'll go into some more detail about each of these steps and into detail on how the scheduler actually represents this LLVM program and decides how to translate it into hardware.